Are you preparing for system design interviews? In that case, this video is a must watch for you. In this video, we will explore the building blocks of system design, such as load balancers, distributed cache, API gateway, CDN, DNS, etc. In today's digital world, where millions of requests flood data centers every second, distributing this load among available servers is crucial. Load balancers play a key role in this, ensuring smooth performance and availability. But what if a load balancer fails? In this video, we will explore the fundamentals of load balancing, essential load balancing algorithms, services offered by load balancers, and most important, strategies to mitigate the impact of load balancer failures. Hi there, welcome to Tech and Career Bytes. I'm a software professional with over 2 decades of experience, including 7 years in leadership roles at a global product based organization. Load balancers act as mediators between clients and servers, ensuring that the incoming requests are distributed evenly across the server pool. Let's explore the fundamentals of load balancing and the invaluable services load balancers provide. Load balancing is the process of distributing the incoming client requests equally among a group of servers. By doing so, load balancers prevent any single server from being overwhelmed, thus avoiding potential server crashes or overloads. Load balancer, situated immediately after a firewall in a data center, ensures optimal performance, scalability, and availability of applications or services. Load balancers offer a range of essential services that enhances the reliability and efficiency of systems. Let's explore each one of them. Load balancers facilitate seamless scaling of applications by adding or removing servers based on demand. This scalability ensures that the system can handle fluctuating traffic without compromising performance. If you want to know more on scalability, you can watch our video linked in the description box. Even in the event of server failures or faults, load balancers ensure continuous availability of services. They wisely route traffic away from faulty servers, thereby maintaining uninterrupted service for end users. Load balancers optimize performance by directing requests to servers with the least load. This minimizes the response time and enhances overall system efficiency. You can learn more about various software performance metrics in our video. Again, the link can be found in the description box. We now understand the benefits of integrating load balancer in our IT infrastructure. But where exactly should we position them after the firewall? Let's discuss that. Load balancers are typically positioned between clients and servers. However, in my extensive 20 plus years of experience in the industry, I've consistently seen the deployment of load balance across multi-tier architectures. Here are those multi-tiers. First, between end users and web servers or application gateways. Second, between web servers and application servers handling business logic. And third, between application servers and database servers. In addition to the core services discussed earlier, load balancers offer a suite of other functionalities that streamline operations and improve system functionality. Let's discuss them. Load balancers monitor health and reliability of servers using heartbeat protocols. This ensures a timely detection of server failures and enhances overall user experience. TLS handshake helps establish a secure connection between client and server. Load balancers alleviate the burden on end servers by handling TLS termination with clients. This improves system performance. To know more about a TLS handshake, watch our video on Pint is the transition to HTTP2. The link is available in the description box. Load balancers analyze the traffic patterns and usage statistics to predict future demand and optimize resource allocation. Through automation, load balancers minimize the need for manual intervention in handling system failures, enhancing operational efficiency. Load balancers facilitate service discovery by routing client requests to appropriate hosting servers based on service registry information. Load balancers enhance system security by mitigating attacks like denial of a service across different layers of the OSI model. Load balancing algorithms are a crucial part of load balancers. They help spread the incoming network traffic among many servers or resources to make sure they work well, stay available, and don't get overloaded. Here are 10 important load balancing algorithms. Round robin is one of the simplest and most widely used algorithms. Round robin evenly distributes incoming requests among the available servers in a circular manner. It does not take a server load or a response time into account, making it suitable for environments with similar server capacities. Weighted round robin is similar to round robin. Weighted round robin assigns a weight to each server based on its capacity or performance. Servers with higher weights receive more requests, allowing for better resource allocation and load distribution in heterogeneous server environments. The least connection algorithm directs incoming requests to the server with the fewest active connections at the time of the request. It is ideal for scenarios where server response times vary significantly or when sessions have varying durations. IP hash uses the client's IP address to determine which server should handle the request. By consistently mapping each client IP to a specific server, IP hash ensures that requests from the same client are always directed to the same server, making it useful for session persistence or stateful applications. Least response time is also known as least time. This algorithm routes a request to the server with the lowest average response time or latency. It dynamically adjusts the traffic distribution based on server performance metrics, ensuring optimal user experience and minimizing latency. The random selection algorithm randomly selects a server from the available pool to handle each incoming request. While simple to implement, it may result in uneven server loads and is generally not recommended for critical or high traffic environments. Least bandwidth directs a request to the server with the least amount of bandwidth usage or network traffic. It is beneficial for optimizing network resources and ensuring efficient utilization of available bandwidth capacity. Agent-based adaptive load balancing algorithm employs agents or monitoring probes deployed on each server to collect real-time performance metrics such as CPU usage, memory utilization, and network traffic. Based on these metrics, the load balancer dynamically adjusts the traffic distribution to optimize server utilization and maintain stability. Similar to least connection, least resource utilization algorithm directs a request to the server with the lowest resource utilization, such as CPU load or memory usage. By distributing load based on server health and capacity, it helps prevent server overload and ensures efficient resource allocation. Chained failover combines multiple load balancing algorithms in a sequential or hierarchical manner to provide fault tolerance and high availability. If a primary load balancer or server fails, traffic is automatically rerouted to backup servers or alternate load balancers, minimizing downtime and ensuring continuous service availability. By effectively balancing the load across a distributed resources using the right load balancing algorithm, organizations can enhance availability, scalability, and responsiveness of their applications and services. One common concern with the load balancer is the risk of them becoming the single point of failure. This raises questions about what happens when load balancers fail and how businesses can ensure continuous operation in such scenarios. Let's discuss Few mitigation strategies. Load balancers are typically deployed in pairs or clusters to ensure high availability and fault tolerance. In this setup, redundant components are configured in the high availability configuration, distributing the load balancing functionality across multiple load balancers. If one load balancer encounters a failure, the other one seamlessly takes over its responsibilities, preventing any disruption to the overall service. Companies use clusters of load balancers to make sure they are reliable and can handle problems. These clusters constantly check each other's health and performance to spot issues early. If one load balancer fails, another one takes over right away, so there is no interruption in traffic routing. This setup makes load balancers very reliable, minimizing downtime and keeping services available all the time. Despite these measures, there is still a slight risk of downtime if the entire load balancer cluster experiences issues. In such rare cases, manual rerouting procedures may be necessary to restore service and minimize the disruptions, especially in critical situations. This may involve troubleshooting the root cause of the issue and implementing corrective actions such as restarting or replacing faulty components. By implementing redundant load balancers and robust failover mechanisms, businesses can mitigate the risk of load balancer failures and ensure uninterrupted service delivery to their users. In conclusion, load balancers play a vital role in today's modern IT infrastructures, ensuring reliability, scalability, and performance optimization. By intelligently distributing the traffic and offering a range of essential services, load balancers empower organizations to provide seamless and efficient services to end users. If you found this video helpful, give us a thumbs up and subscribe to our channel for more interesting tech topics. Also, do check out our other videos on software performance optimization case studies, system design, coding, big data, and career growth. My name is Rupa, and I thank you so much for watching this video. See you next time. Annoyed by slow loading websites during busy times? Frustrating, isn't it? Well, there is a secret weapon companies use to stay speedy: caching. In today's video, we are going to cover almost everything about caching, including its benefits, caching strategies, cache invalidation methods, cache eviction policies, and solutions to some common cache related problems. It's going to be a lot of learning and fun learning. So keep watching till the end. Hi there, welcome to Tech and Career Bytes. I'm a software professional with over 2 decades of experience, including 7 years in leadership roles at a global product based organization. In today's world, users expect lightning fast website, but as the traffic peaks, the performance can suffer, and that's where caching comes in. Consider a popular e-commerce platform experiencing a surge in user traffic during a festive season sale. As the number of users increase, so does the volume of database queries, resulting in sluggish performance and delayed response times. This performance degradation impacts the user experience and may lead to lost sales opportunities for the business. To mitigate the performance issues caused by increased database queries, the e commerce platform decides to implement caching. By caching frequently accessed information such as product details, prices, and availability, the platform aims to reduce the database queries and deliver faster response time to users browsing the website or making purchases. But will the caching really help the e commerce platform mitigate the performance issue? Let's understand how caching works. When a user visits the e commerce platform to view product listings, the system first checks the cache for the requested product information. If the data is found in the cache, it is retrieved quickly and served to the user, resulting in a seamless browsing experience. However, if the data is not present in the cache, the system retrieves the information from the database, serves it to the user, and updates the cache to prevent future incidents of not finding the data in the cache. If the data is found in the cache, it is called cache hit, and if not, it is called cache miss. But how does the desired data get loaded to the cache? And how do we ensure synchronization between the cache and the database? There are several caching strategies that help us keep the data in sync. Let's explore them. Caching strategies are the approaches to manage how data is stored and retrieved in a cache. Let's understand few commonly used caching strategies. In a read-through caching approach, when a cache miss occurs, the system automatically fetches the data from the database, updates the cache, and returns the data to the user. Using memcached for caching of frequently accessed database queries in a web application is an example of read-through cache. In cache-aside caching, when a cache miss occurs, the application directly fetches the data from the database, updates the cache, and returns the result to the user. MongoDB caching frequently accessed user profiles in a social media platform is an example of this caching. With write back caching, data is returned to the cache first and then asynchronously returned to the underlying storage at a later time. This strategy improves write performance by reducing the latency associated with synchronous disk writes. A database system caching write operations in memory before committing them to disk to improve overall system responsiveness and throughput is an example of this caching. In write-aside caching strategy, the data is directly returned to the underlying storage without being cached initially. Only subsequent read requests for the same data trigger caching. This approach is beneficial for data with low access frequency or data that does not benefit from caching. An example of this caching would be a file storage system where large files are written directly to disk without being cached to optimize cache utilization for frequently accessed files. In write through cache, every write operation to the database is also written to the cache simultaneously. This ensures that the cache is always up to date with the latest data. Redis cache with write through caching for user session management is an example of this. Okay, now that we have loaded the data in the cache, how do we ensure that it is still valid and not outdated? Cache invalidation methods confirm that the cached data is in sync with the original source. Cache invalidation is the process of removing or updating the cache data when it becomes outdated. This ensures the accuracy of the cache data. Cache invalidation methods are broadly classified into two: time based invalidation and event based invalidation. Let's understand each of them in detail. Time to live expiration is a time based invalidation method. This method involves setting a time to live value for cached content, after which the content is considered stale and must be refreshed. When a request is received for the content, the cache checks the time to live value and serves the cached content only if the value has not expired. If the value has expired, the cache fetches the latest version of the content from the origin server and caches it. For example, in a news application, articles in the cache may have a TTL of 24 hours. After 24 hours, the articles expire and are removed from the cache. In event-based invalidation, the cached entries are invalidated based on specific events or triggers, such as data updates or deletions. Let's discuss some commonly used event-based invalidation methods. The purge method removes the cached content for a specific object, URL, or a set of URLs. It is typically used when there is a change or update to the content and the cached version is no longer valid. When a purge request arrives, the cached content is removed immediately, and the next request for the content will be served directly from the origin server. Refresh method fetches a requested content from the origin server even if cached content is available. When a refresh request is received, the cached content is updated with the latest version from the origin server, ensuring that the content is up to date. Unlike a purge, a refresh request does not remove the existing cached content. Instead, it updates it with the latest version. The ban method invalidates the cached content based on a specific criteria, such as a URL pattern or a header. When a ban request is received, any cached content that matches the specified criteria is immediately removed, and any subsequent request for the content are served directly from the origin server. Stale while revalidate method is used in web browsers and CDNs to serve stale content from the cache while the content is being updated in the background. When a request is received for a piece of content, the cached version is immediately served to the user, and an asynchronous request is made to the origin server to fetch the latest version of the content. Once the latest version is available, the cached version is updated. This method ensures that the user is always served content quickly, even if the cached version is slightly outdated. After the cache invalidation, it appears that the cache is full and has latest data. But the cache misses have increased tremendously. So, what steps should be taken next? We need to make room for new entries in the cache and reduce cache misses. This process, known as cache eviction, is crucial for optimizing the cache performance. Cache eviction policies determine which items are selected for removal based on a certain criteria. Let's discuss few cache eviction policies. LRU removes the least recently accessed items when space is needed for new entries. For instance, in a web browser's cache using LRU, if the cache is full and a user visits a new web page, the least recently accessed page is removed to make room for the new one. MRU evicts the most recently accessed items to free up space when necessary. For instance, in a mobile app cache, when the cache is full and the user tries to access a new feature, the most recently accessed feature is evicted to accommodate the new data. In a first in first out cache, the oldest items are removed first when space is required. For example, in a messaging app, when the cache is full and a new message arrives, the oldest message in the cache is evicted. Least frequently used caching removes items that are accessed the least frequently. LFU keeps track of access frequency, and when space is limited, it removes items with the lowest access count. For example, in a search engine cache, less frequently searched queries may be evicted to make room for popular ones. Random replacement caching selects items for eviction without considering access patterns. For instance, in a gaming app cache, when new game assets are to be cached, RR randomly selects existing assets to replace. Each cache eviction policy has its advantages and disadvantages, and the choice depends on factors such as applications, access patterns, memory constraints, and performance requirements. The e-commerce platform in our example has now implemented a caching solution, leading to noticeable improvement in website performance. However, several cache-related issues have recently emerged. Cache-related problems occur due to issues such as multiple users or processors accessing data simultaneously, outdated cached data, limited cache size, network problems, incorrect cache configurations, implementation errors, dependencies on external systems, and inadequate cache forming strategies. Let's discuss solutions to few common cache related problems. Thunderherd problem occurs when multiple requests trigger simultaneously cache misses. This could happen when a large number of cached content expires at the same time. As the requests now directly hit the database, it overloads the database. There are two ways to mitigate this issue. One is to avoid setting the same expiry time for the keys. Another approach is to limit database access to essential business data only, preventing non essential data from accessing the database until the cache is operational again. Cache penetration happens when malicious users bombard the system with requests for non existent data. This causes a cache bypass and causes unnecessary load on the back end. One solution could be to implement input validation and rate limiting to mitigate the impact of cache penetration attacks on the system. The cache breakdown problem is similar to the Thunderhead problem. It happens when a hotkey expires. A large number of requests then directly hit the database, overwhelming the system. Since hotkeys make up 80% of the queries, a solution to this problem is not to set an expiration time for them. Cache crash happens when the cache is down, either due to software bugs or hardware failures, and all the requests directly go to the database. There are two ways to solve this problem. One is to set up a circuit breaker, and when the cache is down, the application services cannot visit the cache or the database. The other is to set up a cluster for the cache to improve cache availability. In companies like Amazon, Netflix, Google, Meta, and eBay, caching solutions like Redis and Memcached are usually used for caching dynamic data, and CDNs are usually employed for caching static content. In summary, caching is vital for optimizing the system performance in high traffic environments. I hope today's discussion will help you implement the right caching solution. If you found this video helpful, give us a thumbs up and subscribe to our channel for more interesting tech topics. Also, do check out our other videos on software performance optimization case studies, system design, big data, coding, and career growth. My name is Rupa, and I thank you so much for watching this video. See you next time. You might have heard a lot about API gateway, but do you know how to onboard APIs to an API gateway? In this video, we are going to discuss what an API gateway is, why it is needed, and most importantly, how to effectively onboard APIs to an API gateway. So, stick around for a clear explanation and practical examples. Hi there, welcome to Tech and Career Bytes. I'm a software professional with over 2 decades of experience, including 7 years in leadership roles at a global product based organization. Back in 2012, I was leading the development of an in house API gateway product while my company was transitioning our monolithic e commerce website to a microservices architecture. So, you can imagine how excited I am to talk about API gateway in this video. Let's get started. In today's microservices architecture, where many services interact, managing these interactions efficiently is crucial. The API gateway makes it easier for clients and services to communicate and also solves various other problems in distributed systems. Let's explore the various common challenges in microservices architecture and discover how API gateway simplifies these interactions.
Single point of interaction.
In a microservices ecosystem, the number of services communicating with each other can quickly grow as new features are added, leading to complexity. By serving as the central point of communication, the API gateway streamlines interactions. Instead of services communicating directly, they interface with the gateway, which then manages communication with other services.
Load balancing.
API gateway distributes the incoming traffic evenly across the services, ensuring no service is overwhelmed, thus optimizing the resource utilization. You might wonder, does not a load balancer do that job? We will explore the differences shortly. So stay tuned.
Aggregation of results.
Fetching responses from multiple services can be cumbersome, involving multiple network calls. API gateway aggregates the results from different services, providing a consolidated response to the client, thus improving efficiency.
Security and authentication.
Securing individual services can be challenging and resource intensive. API gateway centralizes authentication and authorization. It manages the security protocols centrally and ensures secure communication between clients and services.
Performance optimization.
Network calls between services can introduce latency, affecting overall performance. By caching responses, API gateway minimizes the need for redundant calls, enhancing performance and reducing latency.
Log collection and monitoring.
Gathering logs and monitoring data from distributed services can be really difficult. API gateway acts as a centralized point for collecting logs and monitoring data. This facilitates a streamlined observability for debugging and improving performance. Apart from solving these common problems in microservices architecture, an API gateway performs many other tasks. Let's discuss them. Before we get into the details, let me emphasize the importance of staying updated and continuously learning in the tech world. With new advancements and innovations emerging every day, it's crucial to keep honing our skills. Check the description box for some learning resources covering coding, system design, and advanced computer science concepts. The API gateway validates the microservice requests and responses and ensure they conform to the expected format and structure. This helps prevent errors and ensure proper functioning of the microservice. API gateway modifies requests and responses for compatibility. It can translate between protocols. For example, if a client sends a request using HTTP1, but the backend service expects a request in gRPC format, the API gateway can translate the HTTP request into a gRPC request before forwarding it to the backend service. Likewise, when the backend service responds with the data in gRPC format, the API gateway can translate it back into HTTP format before sending it back to the client. API gateway provides a consistent way to handle errors. It can generate error responses to clients even when the backend services are unavailable or when services return unexpected results. API gateway caches frequent API responses to improve response time. To learn more about response time and various other software performance metrics, watch our video. The link can be found in the description box. API gateway controls the number of incoming requests to prevent abuse. This helps ensure availability and reliability of the system. As third parties begin using our APIs, it becomes crucial to track their usage for billing purposes. API gateway tracks API usage for reporting and billing. API gateway can be used to discover other available microservices and their locations. This enables the client to access microservices without knowing their specific addresses. API gateway acts as a circuit breaker to prevent a single failed microservice from bringing the entire system down. Cross origin resource sharing management involves handling requests from other domains to ensure security. For instance, a web application hosted on www.example.com making an API request to a server hosted on api.exampleapi.com demonstrates the need for CORS management. When there are multiple versions of a service available, API gateway routes incoming requests to different backend service versions. This ensures compatibility with various client implementations and allows for the seamless operation of multiple versions of the service simultaneously. We have covered so far various functionalities of API gateway. Now, let's see how they all come together with an example HTTP request. Step 1. The client sends an HTTP request to the API gateway. Step 2. The API gateway parses and validates the attributes in the HTTP request. Step 3. The API gateway performs security checks to ensure safe access. Step 4. It communicates with an identity provider for authentication and authorization. Step 5. The rate limiting rules are applied to the request. If it is over the limit, the request is rejected. Steps 6 and 7. After passing security checks, the API gateway determines the appropriate service provider to route the request to by matching its path. We will delve deeper into this process when discussing the API onboarding procedure. Step 8. The API gateway transforms the request into the appropriate protocol and sends it to backend microservices. Steps 9 to 12. Additionally, the API gateway handles errors and faults effectively, leveraging tools like the ELK stack for logging and monitoring. Solutions like Redis for caching enhances performance and reliability. Overall, an API gateway plays a crucial role in simplifying client-server interactions, enhancing security, optimizing performance, and providing a centralized management and control in microservices architectures. Now, let's explore the differences between API gateway, load balancer, and reverse proxies to gain a deeper understanding of their respective roles and functionalities. While load balancers, API gateway, and reverse proxies share the goal of optimizing and managing the web traffic, they each serve distinct functions. Let's discuss them. Load balancer optimizes the resource utilization by distributing traffic among servers. They mainly are used to handle heavy traffic and ensure even load distribution. Load balancers implement a very basic security, unlike API gateway, and it does not transform request and response. Reverse proxy acts as an intermediary between clients and servers, providing security and control. Reverse proxy manages SSL encryption, serves static content, and controls access to internal servers. While primarily forwarding requests, reverse proxy plays a minimal role in load balancing. The table here summarizes the differences between API gateway, load balancer, and reverse proxy. We already have discussed each of these points while discussing the API gateway functionalities. If you have any questions or comments, please leave them in the comments box and I will get back to you. There are several API gateways available in the market, including Nginx API gateway. Suppose we have developed several APIs and installed Nginx API gateway. Now, how do we onboard these APIs and leverage the capabilities of API gateway to maximize API's benefits? Let's discuss the necessary steps. Onboarding an API in the Nginx API gateway involves several steps, including configuring Nginx, defining endpoints, setting up security policies, and configuring the routing roles. Let's dig deeper into each of these steps. Step 1. Nginx configuration. We need to edit the Nginx configuration file nginx.conf to include the necessary configurations for API management. This may involve defining upstream servers, specifying listener ports, and enabling the API gateway module. Here is the example Nginx conf snippet. Step 2. Define API endpoints. The endpoints of our API needs to be defined within the Nginx configuration. This includes specifying the URI paths and methods, get, post, put, delete, etc. that our API supports. Here are the necessary config changes. Step 3. Configure security policies. We then need to implement security policies to protect our API endpoints. This may involve setting up authentication mechanisms, access control lists, rate limiting, and SSL TLS encryption. Here is the example security policy configuration. Step 4. Test and deploy. Once we have configured Nginx API gateway and defined our API endpoints, testing our configuration to ensure that everything is functioning as expected is very important. We then need to deploy our Nginx configuration changes to make the API accessible to clients. Step 5. Monitor and manage. We need to regularly monitor the performance and usage of our API using Nginx API gateways monitoring and logging features. We can manage our API configuration and make adjustments as necessary to optimize the performance and ensure security compliance. By following these steps, we can effectively onboard an API in Nginx API Gateway, providing a centralized platform for managing, securing, and optimizing our API endpoints. In conclusion, API Gateway stands as a cornerstone in modern microservices architecture, simplifying interactions and tackling various challenges of microservices architecture. If you found this video helpful, give us a thumbs up and subscribe to our channel for more such performance optimization case studies. Also, do check out our other videos on technology and career development. My name is Rupa and I thank you so much for watching this video. See you next time. Databases are a big part of system design. When preparing for system design interviews, it is important to know about different types of databases like SQL, NoSQL, and Graph. You should also understand concepts like replication, partitioning, CAP and PACELC theorems, and various data consistency models. In this video, let's explore some of these database related concepts. Do you know how companies like Amazon, Netflix, and Google maintain reliability, availability, and scalability in their large distributed systems? Today, we are diving deep into the world of replication and its critical role in maintaining smooth operation of large distributed systems. Hi there, welcome to Tech and Career Bytes. I'm a software professional with over 2 decades of experience, including 7 years in leadership roles at a global product based organization. Replication in distributed systems is all about creating and maintaining copies of data and resources across multiple nodes. Doing so enhances fault tolerance, improves performance, and boosts scalability. Let's understand what each of these mean. By replicating data across multiple nodes, systems can withstand individual node failures. This improves overall system reliability and availability even in the face of node failures. Replicating and locating data closer to users reduces access latency. This enhances overall performance and responsiveness of distributed applications. We have a separate video dedicated to the topic of software performance metrics. Please watch that to gain more insights. Scalability enables the systems to handle increasing workload and user traffic by distributing the data access and processing across multiple nodes. Please watch our video on scalability to learn more. Now, let's explore various replication types employed in distributed systems. In synchronous replication, data modifications are acknowledged only after they are successfully replicated to all designated replicas. This ensures consistency but may introduce latency and reduce availability. This replication type is ideal for scenarios requiring strict consistency guarantees, such as financial transactions or critical data updates. Asynchronous replication speeds up the response time by acknowledging the data changes before replicating them to all the replicas. However, this can lead to data consistency issues if a node fails. This replication is suitable for applications prioritizing performance and availability over strict consistency, such as content delivery networks or social media platforms. In leader follower replication, one node, the leader, handles all write operations, propagating changes to follower nodes asynchronously or synchronously. This model simplifies the consistency but may introduce bottlenecks and single points of failure. Leader follower replication is effective for systems with a clear distinction between read heavy and write heavy workloads. Multi-leader replication allows multiple nodes to accept write operations independently, propagating the changes to other nodes either synchronously or asynchronously. This approach improves scalability and performance, but requires a conflict resolution mechanisms to ensure consistency. Multi-leader replication approach is often employed in globally distributed systems for replication across distribution centers. In leaderless replication, all nodes are equal peers, accepting read and write operations independently. This model offers high availability and scalability, but requires consensus protocols to maintain consistency. Leaderless replication cannot be synchronous due to the inherent difficulties and compromises involved in achieving synchronous replication without a leader. Leaderless replication is recommended for highly scalable systems with decentralized architectures, where the emphasis is on fault tolerance and horizontal scalability. Amazon uses a combination of multi-leader and leader-follower replication strategies to ensure high availability and consistency across its globally distributed e-commerce platform. Meta utilizes leaderless replication techniques, enabling seamless interaction and content delivery for billions of users worldwide on its social media platform. Google employs a mix of synchronous and asynchronous replication approaches tailored to the specific requirements of its diverse portfolio of services, including Google Search and Google Cloud Platform. In conclusion, replication serves as the backbone of distributed systems, offering solutions to scalability, availability, and reliability challenges. By understanding how different replication methods work and where they are best used, organizations can design strong and effective distributed systems. If you found this video helpful, give us a thumbs up and subscribe to our channel for more such interesting topics. Do check out our other videos on software performance optimization case studies, coding, big data, and career growth. My name is Rupa, and I thank you so much for watching this video. See you next time. In this video, let's explore partitioning, the various partitioning techniques are used in distributed systems, and the benefits of partitioning. Partitioning in distributed systems involves dividing large data sets or workload into smaller partitions for better performance, availability, and scalability. What we call a partition here is called a shard in MongoDB and Elasticsearch. It is also known as a region in HBase, a tablet in Bigtable, a vnode in Cassandra and React, and a vbucket in Couchbase. So, not to get confused, they all mean the same. Hi there, welcome to Tech and Career Bytes. I'm a software professional with over 2 decades of experience, including 7 years in leadership roles at a global product based organization. Let's dig deeper to understand the benefits of partitioning. Partitioning a data set distributes it across multiple nodes or machines in a distributed system. Each node handles a specific partition, enabling parallel processing. This boosts performance and reduces processing time. Partitioning helps evenly distribute the workload across the nodes in a distributed system. This load balancing approach ensures that no single node is overloaded while others are underutilized. This maximizes system performance and resource utilization. Partitioning lets a system scale horizontally. This enables the system to handle more data or users. To know more, watch our video on scalability. Partitioning provides a fault tolerance and high availability. Even if a portion of the system becomes unavailable, The remaining partitions and nodes can contribute to function, maintaining the overall system's availability. Partitioning can also be used to optimize the data locality, where data is stored and processed closer to the computing resources. Data locality minimizes the data transfer across the network, reducing latency and improving the overall system performance. Partitioning techniques vary based on the specific requirements and the characteristics of data and the distributed system being used. Let's discuss some of the common data partitioning techniques. There are two different types of data partitioning: vertical data partitioning and horizontal data partitioning. Vertical data partitioning, also known as column partitioning or column based partitioning, is a data partitioning technique where a table is divided vertically based on columns. In this approach, columns with similar characteristics or access patterns are grouped together in separate partitions. Normalization is one way to perform vertical partitioning. Let's consider an example of vertical partitioning in the context of an e-commerce application that manages customers' information. In a traditional table structure, you might have a single table called customers with columns such as customer ID, name, email, address, phone, and order history. All these columns are stored together for each row representing a customer. With vertical data partitioning, we can partition the table based on the logical relationships between columns. Let's say we decide to vertically partition the customers table into two partitions: personal info and order info. Vertical data partitioning is typically performed on user profile, product catalog, and customer related data in e commerce, and patients' records and medical data in healthcare. In horizontal data partitioning, a table is split into smaller multiple tables, where each table contains a subset of the original table rows. These subsets are then placed on different nodes. Some of the popular horizontal data partitioning techniques are range partitioning, directory based partitioning, hash partitioning, and partitioning based on consistent hashing. We will be discussing each one of these in detail. So don't go anywhere and stay tuned. In range partitioning, data is divided into partitions based on a specific range criteria. Each partition then contains a predefined range of values. Let's consider an example of range partitioning in the context of a sales database. We have a table named sales data with columns order ID, order date, customer ID, product ID, and quantity. To apply range partitioning, we divide the sales data table based on the order date column, which shows when each order was placed. Here is how we split the data into three partitions. First partition, recent orders, containing the last 30 days orders. Second partition, historical orders, which contains orders from 31 to 365 days ago. And the third partition, archived orders, containing orders older than 365 days. Each order is stored in the partition that matches its order date. New orders go into the recent orders partition, and as time passes, orders move to different partitions based on how old they are. Google's Big Table and Apache HBase seem to leverage range partitioning. However, range partitioning has its limitations. In range partitioning, efficient range queries can only be done using the partition key, not other keys. Plus, if a big range spans multiple nodes, query performance suffers. Also, data distribution may be uneven if one range has more data than others. In directory-based sharding, the data items are distributed across the shards based on explicit mappings maintained by a centralized directory or metadata service. This approach is beneficial when there is a need for a centralized control over data distribution and routing in a distributed system. Consider an example of directory-based sharding in an e-commerce sales database. We have a distributed database storing sales orders across multiple shards. Instead of a predefined ranges, a central directory maps each order to a shard based on its ID. When accessing or modifying data, the directory routes a request to the correct shard. Directory-based sharding centralizes control over data distribution, but the directory becomes a single point of failure. Google's Spanner and Amazon's DynamoDB uses directory-based sharding. Hash partitioning divides the data into partitions using a hash function on a column. For example, Cassandra and MongoDB use MD5 as the hash function. Let's consider an example of a hash partitioning a customer database. We have a table called customers with the following columns: customer ID, name, email, and city. To apply hash partitioning, we partition the customers table based on the customer ID column. The partitioning process involves the following steps. First step, determine the number of partitions. Let's say we want 4 partitions. Then second step, define the hash function. Choose a hash function for the customer ID column. Lastly, apply the hash function to each customer ID. This way, each customer record gets assigned to a partition based on its hashed customer ID. Choosing the right partitioning key and hash function is vital in hash partitioning to ensure the data is distributed evenly. Constant hashing is a smart way to distribute data across many nodes without the need to move the data around when nodes are added or removed in the cluster. It works by using a hash function and a circular structure to assign data to partitions. Let's illustrate consistent hashing with an example of a distributed cache system. Suppose we have a distributed cache with 4 nodes A, B, C, and D. Each node represents a partition. The partitioning process involves assigning nodes, where we create a circular ring representing all possible hash values. Each node is placed multiple times on this ring based on its hash value. After that, mapping data. When storing or retrieving data, we hash its key to get a value. This value is then mapped onto the ring to find the corresponding node. Now, let's understand how the partitioning using a consistent hashing works when the cluster changes. That is, when we add or remove nodes from the cluster. If we add a new node like E, its positions on the ring are determined. We adjust the positions between existing nodes to balance the load, minimizing the data movement. If a node fails, like C, its keys are redistributed among other nodes. Only a fraction of keys need to be moved as other nodes take over some of the failed nodes' responsibilities. Consistent hashing is widely used in distributed systems like caches, databases, and CDNs. We have explored data partitioning, but how does the client find the right node to connect to for a request? Also, the allocation of partitions to nodes varies after rebalancing, which the client is unaware of. So, how does the client find the right node to connect to? This is called service discovery. There are a few methods to handle this. Let's discuss them. In one approach, clients can request any node. If it does not have the data, it forwards the request to the correct node. Another approach is using a routing tier. Requests are sent there first, which then directs them to the appropriate node. And the last approach is that the clients already know which partition is on which node and can connect directly. But keeping track of node changes is a challenge. Solutions like Zookeeper help manage these updates. We have a separate video explaining how Zookeeper manages Apache Kafka cluster. Please watch that to learn more. Sharding or partitioning helps systems scale and improve performance, but it adds complexity that may not always be necessary. Here are a few alternate approaches. First approach, vertical scaling, where you upgrade single database server with more resources like CPUs, memory, and storage. This is easier to manage than sharding, yet allows a significant expansion. Second, SQL optimization, where SQL queries and database schema are fine-tuned for better performance. Third, caching. Employ in-memory caches such as Redis to lessen database load by avoiding frequent queries. And fourth approach, use combination of read replicas and load balancer. This offers a horizontal read scalability without full sharding complexity. Also, it distributes reads across replicas. In conclusion, Partitioning optimizes distributed systems performance and scalability. Understanding options like range partitioning, directory-based partitioning, hash partitioning, and consistent hashing enables architects to design robust distributed systems. If you found this video helpful, give us a thumbs up and subscribe to our channel for more such interesting topics. Do check out our other videos on software performance optimization case studies, coding, big data, and career growth. My name is Rupa, and I thank you so much for watching this video. See you next time. Today, we will explore the CAP theorem, strong and eventual consistency, and the PACELC theorem with some real world examples. The CAP theorem states that in the design of a distributed system, it is impossible to guarantee all the three properties consistency, availability, and partition tolerance simultaneously. But do you know that this statement is misleading? That's right, it is misleading. Let's discuss that in detail and understand why we are saying it is misleading. Hi there, welcome to Tech and Career Bytes. I'm a software professional with over 2 decades of experience, including 7 years in leadership roles at a global product based organization. Let's first understand the three properties consistency, availability, and partition tolerance. Consistency ensures all nodes in a distributed system see the same data simultaneously. This is crucial for data integrity. Availability means every request gets a response, regardless of node failures or network partitions. And partition tolerance allows the system to function despite network issues. Network partition happens when the nodes lose connection, causing them to split into separate groups that can't share any data. In any distributed system, network partitions are inevitable. Whether we like it or not, they will happen. When the network is functioning correctly, the system can provide both consistency and availability. And when the network partition happens, we must choose either consistency or availability. Thus, a better way of placing the CAP theorem would be consistent or available when the network is partitioned. A system can either be consistent or available when the network is partitioned. That makes sense, right? Now, if a system chooses a consistency over availability, it means that it prioritizes maintaining a consistent view of the data and may sacrifice availability during network partitions. This is because when the communication between nodes fail, the data in each of these nodes may become out of sync. One or more nodes may have latest data while the other may have stale data. In this case, as we do not want to compromise on the data consistency, the system may refuse to respond to requests until consistency is restored, thereby compromising system availability. Let's understand this better with a real world example. Think of a bank where having the right account balance is really important. If a user withdraws money from an ATM and the transaction gets recorded on one part of the system but not on another because of a problem, the user might see different account balances when checking their balance. This is not a good experience, isn't it? The user may panic. To avoid this, during a network partition, if a user tries to withdraw funds, the system might temporarily reject the transaction until the connection is restored. If a system chooses availability over consistency, it means that it prioritizes remaining responsive and available even during network partitions, but may compromise strong consistency guarantees. In this situation, the system might temporarily allow different or conflicting data states until the consistency is restored. Think about Ola and Uber. They focus on being available so that the users can book the rides easily and the drivers can accept those requests, even in areas with bad internet. During a network problem, if a driver accepts a ride but loses connection before confirming, the system might let them accept another ride to keep the service going. This could cause issues like double bookings or conflicting ride statuses until the connection is fixed. Even with these problems, the priority is keeping the service available for users without interruptions. A distributed system prioritizing consistency over availability offers strong consistency, and a system that prioritizes availability over consistency offers eventual consistency. Let's dive deeper into these two consistency models, strong consistency and eventual consistency. In a system that guarantees a strong consistency, every node in the system sees the same data at the same time, regardless of where the data is accessed. Achieving strong consistency often requires synchronous replication and coordination among nodes. Synchronous replication and coordination among nodes results in increased latency and decreased availability during network partitions. To know more, watch our video on replication. Eventual consistency is less strict than strong consistency and allows a temporary inconsistencies during asynchronous updates across nodes. This approach focuses on keeping the system available and working even if there are network problems. As we discussed earlier, applications that prioritize data integrity and transactional correctness, such as financial systems, may opt for strong consistency despite potential availability trade offs. On the other hand, applications like Uber or Ola may prioritize availability and responsiveness over strict consistency, making eventual consistency a more suitable choice. Just because the cap theorem says either consistent or available does not mean we can't achieve both consistency and availability. Confusing, right? Let's discuss. By focusing on scaling up data centers vertically instead of spreading them out horizontally, we can have both consistency and availability. But the system won't be truly distributed anymore. Since network partitions are unavoidable in distributed systems, it's crucial to decide on the right balance between consistency and availability. Google's spanner database seems to be an exception, though, violating the cap theorem. How? Let's understand that. Google's spanner database system is an interesting case study when it comes to the cap theorem. It aims to provide high availability and partition tolerance while maintaining a strong consistency across its geographically distributed data centers. It achieves this by implementing a unique architecture and leveraging synchronously replicated data across multiple data centers. Now, let's discuss the PACELC theorem. The PACELC theorem is an extension to the CAP theorem. The PACELC theorem states that during network partitions, a distributed system must choose between availability and consistency as per the CAP theorem. Else, when the system is functioning normally without partitions, it must choose between latency and consistency. When consistency is prioritized in the absence of network partition, latency tends to suffer because ensuring consistency often requires synchronous replication and coordination among nodes, which can increase the time it takes for operations to complete. To know more about synchronous replication and its impact on availability, watch our video on replication. In conclusion, understanding the CAP theorem and PACELC theorem helps system designers make informed decisions, ensuring the creation of robust and resilient distributed systems. What will you prioritize in your next project? Consistency or availability? Do let me know in the comment section. If you found this video helpful, give us a thumbs up and subscribe to our channel for more interesting tech topics. Also, do check out our other videos on software performance optimization case studies, system design, big data, coding, and career growth. My name is Rupa, and I thank you so much for watching this video. See you next time. We all rely on the internet for everything, from watching videos to getting work done. But what happens when websites load slowly? It's irritating, right? This is where content delivery networks come into play. In this video, let's explore what CDNs are, why they are needed, and how they work, along with real world examples and optimization strategies. Hi there, welcome to Tech and Career Bytes. I'm a software professional with over 2 decades of experience, including 7 years in leadership roles at a global product based organization. A content delivery network or CDN is a network of servers spread across different locations. A CDN is designed to deliver the web content faster and more reliably to users. It does this by storing content at servers near to users, which helps reduce delays and makes the website load faster. CDNs are needed to address the most common and must to address the challenges of distributed systems. Let's discuss what those challenges are and how CDN helps. By serving content from servers closer to users, CDNs minimize the time it takes for data to travel, resulting in latency reduction, faster load times, and improved user experience. CDNs can handle high traffic loads and sudden spikes in demand by distributing content across multiple servers. This prevents website crashes and downtime and helps websites scale. CDNs improve the reliability of content delivery by reducing the risk of server failures and network congestion. They also provide a redundancy and failover mechanisms to ensure continuous availability. There are a few common terminologies used while discussing CDN. Let's familiarize ourselves with them before diving deeper. A point of presence or POP is a network location where CDN infrastructure is placed to cache and deliver content. For example, Netflix data center located in New York City is a POP among several of its POPs. An edge server is a server at the edge of a CDN network, caching and serving content to users. Edge servers are located at POP. A proxy server is an intermediary server in a CDN that caches and delivers content to users, reducing load on origin servers and improving performance. Proxy servers are also located at POP. Now it's time to go deeper and understand the inner workings of a CDN. A CDN comprises of several components that work together to efficiently deliver the content. Let's first understand the components and then we can see the entire workflow. Client is the end user device, like a laptop or a smartphone that requests a content from the CDN. Routing system determines the optimal path for content delivery based on factors like network proximity and server availability. Scrubber servers filter out malicious traffic and protect against cyber threat like DDoS attacks. Proxy servers cache and serve content to users, reducing the load on origin servers and improving performance. Distribution system manages the distribution of content to edge servers and ensures consistent delivery across the network. Origin servers store the original copy of content and provide it to the CDN for caching and distribution. Load balancers are the components that distribute incoming traffic across multiple servers at various levels to optimize performance and ensure high availability. Content optimization tools improve performance and save bandwidth by preparing and refining content before it is cached and delivered. This includes actions like compressing images, combining files, and minimizing HTML, CSS, JavaScript. For instance, minification trims unnecessary parts like spaces and comments from HTML, CSS, and JavaScript files. Logging and monitoring tools track CDN performance metrics, monitor server health, and provide insights into traffic patterns and usage trends. Management system controls and monitors the operation of the CDN, including configuration, performance monitoring, and analytics. Consider a scenario where a user in India wants to access a popular video streaming website hosted on servers in the USA. Without a CDN, the user's request would need to travel long distances, resulting in slow load times and buffering issues. But with a CDN in place, the workflow is optimized to deliver content efficiently and reliably, leveraging various components of the CDN architecture. Let's see the entire workflow and the role each component plays. Step 1. The end user device in India sends a request to access the video streaming website. Step 2. The request is routed to the nearest point of presence or edge server in India using load balancer to distribute traffic and optimize content delivery. Step 3. The proxy server in the Indian POP checks if the requested video content is available in its cache. Step 4. If the content is available, it is served directly to the user, enhancing performance and reducing bandwidth usage. Otherwise, the request proceeds to the next step. Step 5. The proxy server fetches the requested video content from the origin server in the United States. Step 6. Load balancers are utilized to distribute incoming requests among multiple origin servers, optimizing resource utilization and ensuring scalability. Step 7. The fetched content is then distributed to the proxy server in India as well as to other edge servers or POPs worldwide. Step 8. The content is cached at the proxy server in India for future requests, employing caching strategies. Step 9. The CDN continuously monitors the health and reliability of proxy servers and origin servers, ensuring efficient content delivery and fault tolerance. Step 10. The CDN management system controls and monitors the operation of the CDN, including configuration, performance monitoring, and analytics to ensure optimal CDN performance and user experience. How does the content get loaded to CDN servers from the origin servers? CDN employs various caching strategies to store the content in edge and proxy servers. In push caching strategy, origin servers proactively push content to edge servers before it is requested, ensuring faster delivery to users. And in pull caching strategy, edge servers fetch content from origin servers in real time when requested by users. This reduces storage requirements and ensures freshness of content. The push caching strategy is typically used for static content, and the pull caching strategy is used for dynamic content. To know more about various caching strategies, you can watch our video. The link is available in the description box. We saw earlier that the routing system routes the request to the nearest POP. But how does it do that? As the request for content comes in, finding the nearest server or edge server to fetch data involves determining the server that is closest to the requesting client to minimize latency and optimize performance. Two critical factors influence the proximity of server. The two critical factors are network distance and request load. Network distance is the distance between the user and the proxy server. It depends on two main factors. First, length of the network path. The physical distance between the user and the proxy server determines the network path's length. Shorter paths typically result in lower latency. And second, capacity limits. The capacity or bandwidth along the network path also impacts proximity. Optimal proximity involves selecting the server with the shortest path and the highest available bandwidth. This ensures faster content delivery to the user. Request load is the load on a proxy server at any given time. If a group of proxy servers is experiencing high loads, the request routing system should redirect requests to servers with lower loads. This action helps balance the load across proxy servers and reduces response latency for users. CDNs use various routing techniques to route user requests to the nearest proxy server. Let's discuss a few of them. DNS-based redirection involves mapping domain names to IP addresses of proxy servers located nearest to the client. When a client sends a DNS query to resolve a domain name, the DNS server responds with the IP address of the nearest proxy server, directing the client to that server for content retrieval. Anycast routing is a network addressing and routing technique that directs data packets to the nearest or best performing node among a group of servers that share the same IP address. With Anycast, multiple proxy servers advertise the same IP address, and routers automatically route traffic to the nearest server based on network topology, minimizing latency and improving reliability. Client multiplexing involves maintaining multiple concurrent connections between the client and different proxy servers. This allows the client to connect to multiple servers simultaneously and choose the one with the lowest latency for content retrieval. HTTP based redirection involves the proxy server redirecting the client to a closer server using HTTP status codes such as 301 for moved permanently or 302 for found. When the client sends a request to the proxy server, the server evaluates the client's location and redirects the request to the nearest server for data retrieval. Positioning CDN servers strategically is crucial for efficient content delivery. The CDN server placement can be on premise or off premise. On premises placement involves setting up CDN proxy servers in smaller data centers located near major internet exchange points. These data centers benefit from direct peering with numerous networks, ensuring optimal connectivity and faster content delivery. Off-premises, on the other hand, involves placing CDN proxy servers within Internet Service Providers networks. By leveraging ISP infrastructure, CDN providers can distribute proxy servers across diverse geographical locations, reducing latency and improving content delivery speed for end users. Akamai and Netflix popularized the idea of keeping their CDN proxy servers inside the client's ISPs. What benefits could an ISP get by placing the CDN proxy servers inside their network? Let me know your thoughts in the comment section. Most companies don't build their own CDN. Instead, they use the services of a CDN provider, such as Akamai, Cloudflare, Fastly, and so on, to deliver their content. In a content delivery network, distributing the content to a large number of edge and proxy servers simultaneously while minimizing the burden on origin servers is a critical challenge. To address this challenge, CDNs implement a tree-like structure to facilitate efficient data distribution from the origin server to the CDN servers. In this tree-like structure, the CDN proxy servers are organized into a hierarchy resembling a tree, with edge proxy servers at the bottom and parent proxy servers above them. The edge proxy servers, which are closest to the end users, have peer servers within the same hierarchy. These peer servers receive the data from parent nodes in the tree, which in turn receive data from the origin servers. The data distribution process involves copying content from the origin server to the proxy servers by traversing different paths within the tree structure. Each level of the hierarchy plays a role in propagating content downstream to the edge servers, ensuring efficient delivery to end users. If a child or parent proxy server fails within a POP, the system is designed to handle such situations efficiently. Let's discuss them. In case a child proxy server experiences a failure, DNS can redirect a client request to another functioning child level proxy server within the same POP. Each child proxy server is aware of multiple upper layer parent servers. Therefore, if one parent server fails, the child proxy server can route a request to the alternative parent server, ensuring continuous service availability. Similarly, if a parent proxy server fails, child proxy servers can switch to alternate parent servers to maintain service continuity. This ensures that even if one level of a proxy service encounters an issue, the system can seamlessly route traffic through backup servers. The origin server stores the original content. In case of a origin server failure, the other origin servers within the CDN infrastructure take on the additional load. The content is typically replicated across multiple origin servers, ensuring redundancy and fault tolerance. CDNs use mechanisms like cache invalidation and time to live settings to ensure data consistency between origin servers and edge caches. To learn more, watch our video on distributed caching, linked in the description box. In conclusion, content delivery networks play a vital role in optimizing the delivery of web content to users worldwide. By leveraging a distributed network of edge servers, CDNs reduce latency, improve reliability, and enhance overall user experience. If you found this video helpful, give us a thumbs up and subscribe to our channel for more interesting tech topics. Also, do check out our other videos on software performance optimization case studies, system design, coding, big data, and career growth. My name is Rupa, and I thank you so much for watching this video. See you next time. In this video, we will discuss everything about DNS, an essential component of the internet, including how it works and its design. Hi there, welcome to Tech and Career Bytes. I'm a software professional with over 2 decades of experience, including 7 years in leadership roles at a global product based organization. Imagine you want to visit a website, let's say example.com. Without a DNS, you would need to remember the website's numerical IP address, which might look like 192.0.2.1. Hard to remember such strings of numbers, right? DNS steps in to bridge this gap. The DNS acts as the Internet's directory, converting human readable domain names into numerical IP addresses. Think of it like a digital address book, making internet navigation easier. Let's understand how it works at a high level. We can then dive deeper into its components and design. When you enter example.com into your web browser, the browser first checks its cache for the corresponding IP address. If not found, it then checks the operating system's cache. The operating system facilitates communication between the browser and the DNS resolver. If the IP address is still not found, the browser sends a request to a DNS resolver, which acts as a virtual librarian. The DNS resolver searches its cache for the mapping of example.com to an IP address. If the information is not found in the resolver's cache, it queries the ISP and after that DNS infrastructure for the IP address. You can see the cache usage at various levels in the diagram. Once the IP address is located, it is returned to the browser via the operating system, allowing it to connect to the correct web server and retrieve the desired web page. A DNS resolver could be from your ISP or from DNS providers like Cloudflare's 1.1.1.1 or Google's 8.8.8.8. Let's now understand the various components of DNS. In the domain name system, several key components work together to resolve domain names to IP addresses. Let's discuss each one of them. Name servers are specialized servers responsible for storing and providing DNS information. They maintain databases called zone files, which contain mappings of domain names to IP addresses and other DNS information. Name servers respond to DNS queries from clients by providing the requested information or referring the client to another name server if necessary. These name servers are structured hierarchically. We will discuss the details later in this video. Resource records are the fundamental data elements stored in DNS zone files. Each domain has its own zone file, typically stored on the name servers responsible for that domain. Each resource record represents a piece of information associated with the domain name. As seen earlier, DNS uses caching at different layers to reduce request latency for the user. Caching plays an important role in reducing the burden on DNS infrastructure because it has to cater to the queries of the entire internet. DNS name servers are structured hierarchically. This allows for scalability and efficient query resolution. There are primarily four types of DNS name servers. Let's discuss each one of them. DNS resolvers initiate the querying sequence and forward requests to other DNS name servers. Typically located within the user's network, these servers can also serve users' DNS queries through caching techniques. These servers are also known as local or default servers. Root level name servers handle requests from local servers and maintain name servers based on top level domain names like .com, .edu, .us, etc. For example, if a user requests the IP address of example.com, root level name servers will provide a list of TLD servers holding the IP addresses of the .com domain. There are 13 logical root name servers named letter A through M with many instances spread throughout the globe. These servers are managed by 12 different organizations known as the root server operators. Here is the list of those 12 organizations. These organizations are responsible for operating and maintaining the infrastructure of the root name servers. Top level domain name servers store the IP addresses of authoritative name servers. When required, they return a list of IP addresses belonging to the authoritative servers of the organization. Authoritative name servers belong to the organization and provide the IP addresses of web or application servers. They serve as the final authority for DNS resolution within the organization's domain. How are DNS names processed? For example, will example.com be processed from right to left or left to right? Can you guess? Here is the answer. The DNS names are processed from right to left. In the case of example.com, the DNS resolvers resolve the .com part first, then example, and so on. Now, let's explore how the DNS query resolution happens. In DNS query resolution, there are two main methods, iterative and recursive. Let's discuss each. In iterative resolution, the DNS resolver sends a query to root level name server and awaits either the requested information or a referral to another top level domain name server that may have the information. If the queried TLD name server lacks the requested information, it returns a referral to a different name server. The resolver then sends a new query to this referred name server. This process repeats until the resolver either receives the requested information or reaches the authoritative DNS server. In recursive resolution, the DNS resolver sends a query to a root name server and expects a comprehensive response containing the requested information. If the queried root name server lacks the information, it recursively queries other DNS servers, such as TLD and authoritative name servers, on behalf of the resolver until it obtains the requested information. The DNS resolver's configuration determines whether it performs recursive or iterative resolution. We saw earlier that the DNS query results are cached at various levels. Let's go a bit deeper. Caching occurs at various levels, including browser caches, OS caches, DNS resolver caches, as well as caching at the ISP level and across various tiers of DNS name servers. Web browsers often cache DNS records locally to reduce DNS lookup times for frequently visited websites. When a user visits a website, the browser may store DNS information in its cache to expedite future visits to the same site. Operating systems can also cache DNS records to improve system performance. OS level DNS caching stores DNS query results locally, reducing the need for repeated DNS lookups for frequently accessed domains across different applications and services running on the system. Caches maintained by DNS resolvers, such as those provided by ISPs or DNS servers, also store recently resolved DNS queries. Domain name server caches are maintained by name servers at various levels to store recently accessed resource records for the domains they are authoritative for. Root name servers, top level domain name servers, and authoritative name servers all utilize caching to improve DNS resolution efficiency. In essence, DNS serves as the Internet's address translation service, converting user friendly domain names to machine readable IP addresses. Without DNS, navigating the Internet would be like finding your way in a foreign city without a map or street signs. This would have significantly complicated online communication and accessibility. Thanks to DNS, we don't have to face that difficulty. If you found this video helpful, give us a thumbs up and subscribe to our channel for more interesting tech topics. Also, do check out our other videos on software performance optimization case studies, system design, coding, big data, and career growth. My name is Rupa, and I thank you so much for watching this video. See you next time.